Hello everyone, this is allLogarithmsWereCreatedEqual. Here are some mathematical proofs that I'd like to share with you. The first is, in fact, a proof of Euclid's second theorem, but I've recently gained a new understanding of it that I'd like to share. We start with a construction that is the following mathematical product. The product, for all p, where p is a prime number, of 1 over the quantity 1 minus 1 over p. Now this product turns out to be a very interesting construct, and if you'll bear with me, you'll find out why. We can view this function of p as if it were a shorthand value of a convergent geometric series, since it is in the form 1 over 1 minus r. To prove this, if you haven't already seen the proof, or perhaps you've forgotten it, but just consider actually S sub n, because we're talking about the first n terms of a geometric series S. So, by definition, it must be equal to 1 plus a squared plus a cubed plus a to the fourth plus, of course, following this pattern, a to the n. So we keep going. This is just sort of the definition of a geometric series. We're just multiplying each term by a to get the next term, because that's the common ratio, I suppose it's called, or whatever you want to call it. That's just the definition of a geometric series. What we can do from here is actually multiply each side of this equation by the quantity 1 minus a. So what we do is we can actually say quantity 1 minus a. So, and another way of thinking about this is really what we're doing is we're taking S sub n and subtracting a times S sub n. So just note that this is a correspondence. This is an equality that we'll make use of later on. But for that matter, let's study what a times S sub n is. So we can say, for all these terms in S sub n, we're going to multiply by a, because we're multiplying each side of this original equation by a. So a times S sub n can be seen as a plus a squared plus a cubed plus a to the fourth plus a to the fifth plus all the way up to a to the n plus 1. Now, of course, we can subtract a times S sub n from S sub n and see what we get. The fifth plus all the way up to a to the n plus 1. And we're subtracting them. So this is a nice way of viewing it, because we have S sub n minus a S sub n being equal to, well, as I'm sure you'll notice, most of these terms cancel out, in fact, because we have 1 plus a squared. Well, we also have an a squared, and a cubed, and they line up and they cross out in this sense, because we're subtracting one equation from the other. So 1 plus a minus a plus a squared minus a squared plus a to the a cubed minus a cubed plus a to the fourth minus a to the, they all cross out. That is, all the way up to a to the n plus 1. This one stays, because there's nothing to cancel it out in the first equation. So what we eventually end up with, obviously, is 1 minus a to the n plus 1. And of course, from here, what we can do is factor out an S sub n on the left hand of the equation. So this is S sub n times 1 minus a equals 1 minus a n plus 1, a to the n plus 1. And now, of course, from here, we can divide out both sides by 1 minus a, so we can get 1 minus a to the n plus 1 over 1 minus a, which is, as many of you know, a shorthand formula for evaluating any kind of geometric series, assuming it converges. And, of course, it converges whenever absolute value of a is less than 1. And in fact, we can kind of simplify this when it does converge, and we can simply say that the limit as n approaches infinity, so basically what is the limit as n approaches infinity of this series? So now we're talking about not just a partial sum, but the entire sum, at least theoretically, if it does converge. So we can say the limit as n approaches infinity of S sub n, or we can really just call that the sum of the series, assuming it converges, equals 1 over 1 minus a. So that's just the proof that I wanted to show you. But I suppose this is a bit of a tangent. The original point, of course, was that for this term, in this construct here, it is of that form. It is of the form 1 over 1 minus a, where a, you'll note, is equal to 1 over p. And so, what we can do is we can actually change this product, or change this construct from being a product, where p is a prime number of this, to a product of a sum, basically. And so let me write that out. What we know is that this product becomes the product of a sum. And this sum, you'll note, is equal to, it's going to be of 1 over p to the k, starting with k equals 0 and going to infinity, because we're considering it as an infinite geometric sum, a convergent geometric, where p is, of course, a prime number. It's every prime number. And what's interesting about this structure is that if we expand it out more, we can see that because we're multiplying this sum for every possible prime, and we start with k equals 0, the resultant sum must include all possible primes and all possible powers of primes being multiplied together. And what do we get when we take all possible products of prime powers? Well, and this relates to the fundamental theorem of arithmetic, we end up with all the natural numbers n. So this structure, in fact, equals the sum of the reciprocals of all the natural numbers, n, which is known as the harmonic series, a famous divergent series, which you can hear me talk about in this other video I made. I'll leave a link, hopefully. If I forget, be sure to remind me. And thus, this proof is demonstrating that because there are an infinite number of natural numbers n, and more specifically, because this series right here diverges, which we know it does, it's a known divergent series, there must, therefore, be an infinite supply of prime numbers to generate these numbers in the product. So because this sum is infinite and divergent, we know that there must be an infinite number of prime numbers to make this product also diverge. And back to the main point, this proof kind of more directly links the fundamental theorem of arithmetic with the infinitude of primes. And according to Goldstein in an article published by the MAA, this proof, which the Swiss mathematician Euler developed in the 1700s, kind of set a precedent of using ideas in mathematical analysis to prove theorems regarding prime numbers. And now let's take a look at what this product really is, if we were to evaluate the first few terms. Because I just wanted to show you, if we focus on this product by itself, what we can do is expand it and say, well, this is 1 over 1 minus a half times 1 over 1 minus a third times 1 over 1 minus a fifth, because that's the next prime number, times, and we keep doing that, on and on. And from here we can simplify it, and so I'll just do that. It's pretty clear that in each denominator here we want to find a common denominator, a common multiple of the two numbers in the denominator, so we can simplify it more. So in this case, we get 2 over 2 minus 1/2, so it's just 1 over 1/2. And in this case, 1 minus a third is 2/3. 1 minus a fifth is obviously 4/5, and we keep doing that indefinitely, or as long as we feel like it. And of course, from here we can simplify it even further because we just have 1 over a fraction, so we just take the reciprocal. We keep taking the reciprocal for each term. So it's going to be 2 over 1 times 3/2 times 5/4 times 7/6 times 11/10, all the way on and on and on. And we can simplify that, of course. And we end up with 3 times 5/4 times 7/6 times 11/10, on and on and on. And the pattern we're seeing is that the arbitrary term, the general term, is basically a prime number p divided by p minus 1. Which is very interesting, because we know that basically the value of each of these terms in the product will be greater than 1. It'll be some number, it might approach 1 in the general case as we go to infinity, but it will never actually equal 1. It's going to be greater than 1 for each term of the product. And so that kind of helps explain why it diverges, but we need a key point, which is the fact that there are an infinite number of primes as well, to demonstrate that. So sure, each product is a little greater than 1, but there are an infinite number of primes as well, so that kind of solidifies the proof that this product diverges. Or it doesn't really, I mean, this is just an empirical demonstration of that. I just wanted to show you that to get a better sense for what this product is. So if and only if there are an infinite number of primes, this product is infinite and diverges. And this is exactly what Euler proved by linking it with 1 over n. This whole structure, by the way, is known as the Euler Product. And Euler related it directly to the harmonic series, which is this sum, as I mentioned before. I'm gonna do another proof, a proof related to this idea that centers on the sum 1 over p for all primes p. A natural question that arises is, since there are an infinite number of primes, if we take the sum of the reciprocal of each prime, forming an infinite sum, does that sum converge or diverge? Stay tuned and I'll let you know. Thank you all for watching. See you later.